Hello everyone, welcome to the GGM YouTube channel. So this week we will be covering number bases, and particularly non-decimal number bases. So let's just get into it. So a number base is essentially a mathematical notation that's used to represent numbers, using digits in certain places to represent different numbers. So the number base we use every day is base 10, or the decimal base system. So the rightmost digit is the units digit and represents the numbers from 0 to 9. The next is the tens digit that represents 0, 10, and all the way to 90 and so on. And you'll notice that each digit is a different power of 10. So the last digit represents how many of 10 to the 0 we have, and then the next is how many of 10 to the first power we have, and then the next is 10 to the second, and so on. And of course, we can't go over 9 in our last digit, because if we do, then that's included under 10 to the first. So we just put that in there. And that's why we sort of carry numbers when we add things, right? So one number base many of you probably have heard of before is binary, which has usage in computers, right? Because computers have bits that can either have an on or an off state. And binary works similarly. It has only two digits, zeros and ones. And like in base 10, it has a units digit, which is either 0 or 1 units, right? So 2 to the 0. Next, it has a twos digit, which with either a 0 or 1 twos. And then the next with 0 or 1 2 to the seconds, and the nth digit with 0 or 1 2 to the power of n minus 1s. So, for example, if we look at the following number in base 2, 11011, and numbers in different bases will have a subscript after them that tells you what base they're in. So I'll give you 5 seconds to try this. Okay. So we have the number 110101. I think this should be fairly simple. So first you have 1 times 2 to the 0. And then we have 0 here, so we don't really care about that. And then next we have, well, we have 0 times 2 to the first. And then we're going to add 1 times 2 to the second, and then plus 0 times 2 to the third. And then we're going to add on 1 times 2 to the fourth, plus 1 times 2 to the fifth. So it's going to end up equaling this. Right? And if you calculate this out, add all of these together, this is going to end up equaling 53. So, here's a few base problems to try for yourself, so you can pause the video if you so please to try to figure these out, and we'll go over them in about 5 seconds. Okay, so we have a bunch of base problems, and a lot of these have certain tricks to them. In math competitions, you're going to see tricks where you don't have to evaluate the entire thing. You only have to evaluate a simpler thing after you find a strategy to do it. So our first problem is we want to convert 1 of 1 base 2. Okay, so this is fairly simple. So there's no real trick to this. We just do 2 to the 0 plus 2 to the first, and then we have 2 zeros, right? And then we're going to add 2 to the 4. So this is, of course, just going to equal 19. Nothing special here. Now, for the next problem, 1111111 base 2, if you might have tried to compute this by hand. And if you did, well, that would be 2 to the 0 plus 2 to the 1 plus 2 to 2, and you're just going to keep adding these powers of 2 until you get to 2 to the 6th, right? But in reality, there's a much simpler way to do this. So first of all, if you just add 1 to this number, you're going to see that we're going to get 1, 0, 0, 0, 0, 0, 0, 0, because it's reached its maximum with 7 digits. It cannot have any number larger in base 2 with these 7 digits. So when we add 1, it overflows all the way to 8 digits, much like how we carry the 1, for example, when we add numbers in base 10. So if this is what's happening, then, well, we can calculate this, right? And because this is the 8th digit right here, and there's a 1 and nothing else, well, this is just 2 to the 7th. However, we have to subtract 1, so we have 2 to the 7th minus 1, and that's our answer. And this will be 28, so this will equal 127, and that's our answer. And something very similar goes for the following problem, which is very, very similar, except it has only 6 zeros at the end. But this is similar, right? So this is the 7th digit, right? So we have 2 to the 6th right here. Always make sure this is the 7th digit, but it's the 6th power, because the last one is 0. Remember, you always start from 0. If you go from 0 to 6, there's 7 numbers here. 7 numbers here. Right? So you have to be careful for that. But this is just going to end up equaling 64. So that's our answer there. And finally, we are asked to convert 1025 to binary, right? So we want to convert this to some number in binary, all right? And if you're acute, you'll notice that 1024 just so happens to equal 2 to the 10th, right? And this can obviously be used to our advantage. We're going to have 1 as the 11th digit, right? Not the 10th digit. Remember, there's always a 0. So we're going to add 10 zeros at the back. And you'll notice that we have 1024. Now we need to add 1, right? Because it's 1025. So we just change the last 0 into a 1 when we add that 1. And we have our answer. Now, hexadecimal is a number base that is also commonly used in both computing and math competitions. If you've ever seen a hex code, that is what the computer is using. The computer is taking a hexadecimal number, and that's what a hex code is, to represent what color it wants, right? Because it uses hex codes to determine which color you're trying to choose. So hexadecimal is base 16. So this time there are 16 different digits to use because we are incrementing by powers of 16 instead of powers of 10. Therefore, we're going to have digits 1 to 0, 1, 2, all the way to 9, but we can't just stop there, right? We have to have more because we have things that are higher than 10 that aren't multiple digits. So we have A, which equals 10 as a digit, B as a digit, which equals 11, and then we have this all the way to F, which equals 15, right? We can't have anything equaling 16 because then that would just be 1, 0, base 16. That's what 16 is in base 16, right? So since we're working in base 16, we can have any number smaller than 16 in a single digit. So I'll give you 5 seconds to compute the following. So okay, let me just make a new sheet there. So we know that 5, 6 AD, we want to convert this from base 16 to decimal, right? Okay, how are we going to do that? So first, let's just make sure we know A is equal to 10, right? And D is going to equal 13, right? Okay, so now we're going to have, what, D is the last digit, and that's just 13, right? So that's our last digit over here. Okay, what are we adding to that? Well, next we're going to add a times 16 to the first power. So we have 16 to the first power times 10. And next we're going to have 6 times 16 squared. So this is going to be 16 squared. And finally, we're going to have 5 times 16 to the third. Right? We're all just going by the powers of 16. And these are definitely not the easiest things to calculate. I think you can just, okay, so, well, this is 2 to the 12th, right? And that's going to be 4096. So, you probably won't see anything this bashy on the AMC8, especially not on the AMC8. Like, you might see something, like, pretty bad on AMC10, like, very rarely, but you're not going to see anything like this on the AMC8. So, yeah, that's a little bit questionable, but, this is going to be 56 times 6 plus 16. So if we actually add all of this up, this is going to be, so I guess, like, now it's about time I can show, like, a trick you can use to calculate. You know that 4096 is just equal to 4100 minus 4, right? Times 5. So all you have to do is calculate 5 times 4100 minus 20. And of course, this is going to be 20500 minus 20, right? So this is going to equal 20480, right? And then this, pretty sure you can just multiply this one out yourself. This is like 1536, I think. Feel free to skip this section if you don't want to go over all the calculation. That's totally understandable. So if we add all of these things together, we're going to get 22189. And that's our answer. So you can see how numbers scale much faster in base 16 than base 10. Generally, of course, numbers in a higher base will have much larger representations in lower bases. And of course, we have our other question with converting 4095 to hexadecimal. And I think you might have seen from this that 2 to the 12th is indeed 4096, so we just want 6 to 16 to the third minus 1. And take note, remember how we said that f is equal to 15, right? So if this is 16 to the third minus 1, remember, this is the minimum 4-digit hexadecimal number. So if we're subtracting 1, we're going to go from that to the maximum 3-digit hexadecimal number. And that is going to be FFF, just 3F. And that will be our answer. Sorry if this F looks disconnected. Yeah, that's our answer. Now, we also have other just non-decimal bases in general. It doesn't have to be base 2, base 16, or any number in specific. These can be pretty much any number, but they start from 2 and increase, right? So they're not going to have anything less than 2, and it's probably good to chew on why there's no base 0 or base 1, or even base -1, really. If you want to think about that, then go right ahead. So in base n, for some positive integer n greater than 2, of course there are also non-integer bases. There's even factorial bases. But for the purposes of this video and use for math competitions, we're only going to go over positive integer bases, or radixes as they're called, that are greater than 2. So a number x expressed in base n will consist of some number of the maximum integer k, such that x is greater than or equal to n to the k, right? Because we don't want our n to the k to be larger than x, right? That just doesn't make sense, because then we would have to have negative digits, which doesn't really make sense. So we can subtract as many of these as we want until the number we have is too small to subtract another n to the k. And then we do the same with n to the k minus 1, and so on. So we're going to have the form x is equal to some coefficient a sub k times n to the k plus a sub k minus 1 times n to the k minus 1. And you're just going to keep adding until, of course, you get to a sub 1 times n plus a sub 0, where a sub I, whatever I may be, right, between 0 and k, inclusive, is a positive integer ranging from 0 to n minus 1. Or actually k minus 1, sorry. Or no, it would be n minus 1, yeah. There's a mistake in there, actually. No, there isn't. Okay. Where a sub I, where I is between 0 and k, is a positive integer ranging from 0 to n minus 1. And it's pretty useful to think about why this is, so I'll give you 5 minutes. Or seconds, sorry. Well, okay. Well, I hope you spent 5 minutes pausing the video and thinking about it, or not, because this is not really that difficult of a concept. So, basically, if we have as many, if we have n to the power of k is less than or equal to x, that means that n to the power of k plus 1 is going to be greater than x, right? And because of that, we're not going to be able to subtract more than n minus 1 n to the k's, because if we subtract n times n to the k, or anything more than that, well, we're going to be subtracting n to the k plus 1, and that will not be very efficient, because x will be less than that, right? So we don't want to do that. So it's going to range from 0 to n minus 1, because, again, this concept of overflow, if it goes to n, you're just going to overflow into whatever the next digit happens to be, right? So you can't have anything greater than n minus 1. So when converting from one base to another, it's best to use base 10 as a sort of intermediate step. So, for instance, let's say that we want to convert 3464 base 7 to base 3, which is also called ternary. We can see that this is just equal to, using the concept that we just talked about, 3 times 7 to the third plus 4 times 7 to the second plus 6 times 7 plus 4. And that's equal to 1271 in base 10. And now we want to convert that into base 3. So the maximum power of 3 that fits in this number is 729. And after we subtract that, we can't subtract 729 anymore, so we turn to 3 to the 5th. And we can subtract this twice from 542. So after we subtract 2 of those, we're going to get a 56. And going to 3 to the 4th equals 81, we can see that 56 is too small to take away any 81s. So the place for 3 to the 4th is just going to be 0, because we have 0 of those in our number. Now, 3 to the third is 27, and we can take away 2 27s, so we have 56 minus 2 times 27 equals 2. And we can't subtract any 3 squared or 3's, because those are both greater than 2, so those are also 0. We don't have any of those. And we can subtract 2 1s. So our number in base 3 is then 1202002. So you can see the entire representation down here. where it's just r powers of 3. And here's some just base conversion problems. I'll give you 5 seconds to pause the video and do some of these. Some of these are quite tedious. Okay, so it's fine if you didn't do all of these because honestly these are quite tedious. But I'm just going to go over the first two just to create a good example. So the first problem has us wanting to convert this to base 5, right? We're going to expand this into what? 1 times 8 to the third plus 2 times 8 to the second plus 7 times 8 plus 6. And if we calculate all of that out, this is going to become 5, 1, 2. This is going to become 1, 2, 8. This is going to become 56, and this is going to be 6. So, adding that should get 702. The fact that these add together for 640 might help you substantially, right? So we have 702 in base 10, and we want to convert this to base 5. So what's the largest power of 5 that goes into 702? It's going to be 625, which is 5 to the 4th, right? Okay, so if we subtract that once, we're going to get 77. And from 77, we can subtract, well, we can't subtract 125, that's too much, so we can subtract 25. So we can subtract 3 times 25, that's equal to 2, right? So first of all, we already have 1, right, for 5 to the 4th. We know there's 5 places here. This is a 0 for 5 to the 3rd, and we know there's 3 of 5 squared. And there's 0 of 5 to the 1st. We don't have any 5s that fit in here, right? And finally, we have 2. So our answer is just going to equal 10302 base 5. And we also have another problem. So 570. That 7 does not look very good. And base 14, and we want to convert this to base 16, or hexadecimal. So recall that b is going to be 11, right? If you're not sure, you can just start off with a equals 10 and then count up from there, right? And then we have 11 plus 7 times 13 plus 5 times 14 squared. So this would be 11 plus, well, 7 times 14 is really just the same as 49 times 2, right? So that's going to be 98. And 14 squared is 196. And again, we can use that trick I taught you before, right? This is just equal to 200 minus 4. So you would just do 1000 minus 20 for this, and you're going to get 980. And if you just add all of those together, you can get 1089. And that's our base 10 representation, but we want to turn it to something in terms of base 16. So greatest power of 16 that goes into here is going to be 126, right? So how many times can we subtract, 256, what am I saying? Right, this is equal to 16 squared. So how many times can we subtract this? Well, it turns out we can actually subtract this 4 times. I think you might have predicted that. So we have 256 times 4 is going to be equal to 1024. And if we just subtract that, we're going to from 1089. Okay, I'm starting to run out of space, so just right up here. We're going to get 65, right? And from here we can subtract 4 of 16, right? I think that should be fairly obvious because, 4 times 16 is just 64. And we're going to get 1. And then our last digit is, of course, 1. So we have 4, 4, 1, and that is our answer here. And the rest sort of go by similarly. Now, number-based problems appear frequently in contests like the AMC 8 and the math counts. So here's a number-based competition problem. So what is the least positive base 10 integer that can be written as a 4-digit number in base 3 and a 3-digit number in base 4? So think about the smallest number that is a 3-digit number in base 4 and a 4-digit in base 3. So this one's for math counts. I'll give you 5 seconds. Okay. So this one's really not that difficult. You just have to consider minimums. So we want, what is the smallest number that can be written as a 4-digit number base 3? Well, that's going to be 1000 in base 3, right? And of course, this is just going to equal 3 to the third equals 27. And so now we can think about what is the smallest number that can be written in 3 digits in base 4. And that's going to be 1004. And the point is that we want to find whichever is smaller, and then, well, we want to find whichever is greater. Because if we have 2 ranges, whatever's in the more specific range is the one that's going to work. So this is going to equal, what, 4 squared equals 16. So we can clearly see that 27 is larger, so 27 is our answer. And just for more explanation, the largest number that can be written in base 4 is 333. And this is going to equal 64 minus 1, right? So this is 63. So 27 is within this range, and we want the smallest number that can be written as a 4-digit number in base 3 and a 3-digit number in base 4. Since the smallest number that can be written as a 3-digit number in base 4 is smaller than the smallest number written in 4 digits in base 3, this is a more specific range, right? If we go to 26, this is not going to be 4 digits in base 3 anymore. So 27 is both in between this range and also the minimum in this range. So that's why it's the answer. And here's 2 more base problems from the AMC and math counts. I'll do the first one, and I'll let you figure out the second one by yourself. So I'll give you 5 seconds for the first one. Okay, so the base 9 representation of a positive integer is AB, and its base 7 representation is BA. What is the integer expressed in base 10? So we have AB in base 9. Oh yes, and also these are not the hexadecimal digits we saw before. These are just variables. We're trying to find what A and B equal, just to clear up any confusion there. So this could equal, this is equal to 9A plus B. I don't know why I wrote an equal sign there. It's supposed to be plus sign. B. 7B plus A. And we know that this is the same number, so we have 9A plus B equal to 7B plus A. So we have 8A is equal to 6B. And so we have what? 4A equals 3B. And so you'll notice that, well, we can have A equals 3 and B equals 4, right? That is the smallest possible solution for this. But we also have, we can have, oh, I don't know, A is equal to 6 and B is equal to 8, right? Any set of numbers, or is right now, at least, what it looks like, is any numbers that satisfy this ratio right here are going to work. But see, that's not true, because we can express these two numbers as digits in base 7, which means that both A and B are going to be less than 7. So we can clearly see that under those conditions, this is the only one that works. So A is 3 and B is 4. And you can plug this into whichever of these equations you want. But we can have 28 plus 3, right, is going to equal 31. And that's our answer. So this is pretty much all for today. I did have some other stuff I wanted to cover, but I didn't want the video to get too long, so I might include some of that as something in this week's weekly problem. With that settled, I think we're pretty much done for this video. So thank you everybody for tuning in, and I'll see you next week. Bye.